Welcome to this Toronto branch CASI meeting. My name is Todd from CASI headquarters, and I'm here with my colleague April from CASI headquarters. We will be in the background helping you if you have any technical issues. We ask that all participants please leave their microphones and cameras off for the duration of the event, and instead use the chat feature. All questions can go into chat, comments can go into chat. Our moderator will be collecting questions and posing those questions to our presenter at the end of the session, and they'll make an attempt to answer everything that's come in through the chat. Again, please leave your cameras and mics off, and I would like to now pass over the floor to Chris Hayball, the chair of the Toronto branch. Take it away, Chris.
Thanks, Todd. Good evening, everybody, and welcome to the March meeting of the CASI Toronto branch. Perhaps I should say good afternoon now that we're on daylight saving time. It's lovely and light out now, so that's nice. Wherever you are, good afternoon, good evening. Thank you for joining us. I'll jump right into the topic for tonight by introducing our guest speaker. Bill Zwolinski is coming to us from Kistler. He has a Master of Science in Electrical Engineering from the University of Connecticut, specializing in signal processing and controls. Bill worked over 15 years in research, development, test, and evaluation, including underwater acoustics for the Navy Laboratory, as well as Chief Engineer for Navy Carrier Landing Systems at Textron. Bill also has MBA from the University of Phoenix, specializing in technology management and marketing, and has held positions as General Manager, Product Manager, and Sales Manager at Kistler. Currently, Bill is the Business Development and Application Manager at Kistler for the Americas region and is heavily involved in helping engineers solve their measurement problems. Bill is normally based in Buffalo, but tonight he's coming to us from Portland, Oregon. So big welcome to Bill.
Thank you, Chris. Appreciate that. Let me just share my screen. Hang on. Yeah. Okay. Okay, can everyone see my screen? Yeah. Okay. Okay, thank you so much, Chris and Todd, for the introduction and the opportunity to address CASI. Thank you. So the host is start my video. Hang on. There we go. So we're going to talk about piezoelectric technology and how it relates to the aerospace industry, in particular the space industry. Okay, so we're going to continue and just give you a brief agenda overview. I'm going to talk a little bit about piezoelectric principles of operation, measuring chains. We're going to talk a bit about force and vibration. Some applications we're going to talk about: micro vibration, force limited vibration, propulsion testing, payload test, and then we'll wrap up with some summary conclusions. And I'm certainly eager to answer any questions that you might have, so please feel free to send them in. It's always good, I think, to start out with a sort of like an application that, you know, everyone sees these launches nowadays, and it's pretty impressive to see the complexity. I mean, this Mars landing was just phenomenal, in my view, just the technology behind all that, and pretty impressive. But, you know, NASA is also looking at, you know, a heavy lift capability with the Orion program and the SLS. So part of the challenge there is that, you know, back in the you know, 60s or 70s, 80s, even 90s, there's been accidents that have occurred due to you know, faulty equipment, and they want to make a way to get the astronauts away from that situation. So a lot of times that happens early on in the flight. So what they have here is, on this stage here, you'll see this attitude control motor. It's basically eight nozzle thruster that basically is going to you know, get the crew vehicle away from danger, and that's really its function. So we work with a company called Northrop Grumman, and they have this video on YouTube, and it's a solid propellant gas generator, and there's 8 ports, basically a proportional valve sequence. And I'm going to let it play for a bit and then come back to it. It's quite loud, but then I'll explain a little bit. But it's basically a typical thrust test, and on the bottom is a force dynamometer to measure forces and moments. So on that basis, these force sensors are integrated into the bottom platform, and their basic function is to measure the forces and moments caused by this thruster valve sequencing to vector the attitude control part of the rocket away from the dangerous region. So it's really, I think, a very typical test. A lot of times we can't get our hands on some of this video because they're testing things that aren't so public. But luckily, this was made public in YouTube, and we can see that how companies will go after this. And mounting the dynamometer in the base is usually very common, and the thruster action is above, and it's isolated from any heat or any issues caused by that. But this is a very typical piezoelectric application. Now, it's also a very typical strain gauge application too. So I'm going to just touch upon that in a minute too, because some folks are more familiar with strain gauge technology. But in terms of piezoelectric instrumentation, we're going to primarily focus on force with some acceleration, some pressure in this presentation. So basically what piezoelectric means is that you have a material in the sensor, and this material is actually a material that if you stress mechanically, it provides an electrical output. So basically a piezoelectric material is mechanical to electrical. Okay, so a sensor designer is wanting ways of relating a measurand, force, pressure, acceleration, to act on this piezoelectric crystal so that you get a proportional output to that measurand. So, and that's the concept behind it. You can certainly go into multi-components, as you see here in force. There's 3 different components, MX, MY, MZ. And then you can certainly go into multi-components in acceleration as well. Not so much in pressure. It's usually independent sensors. In terms of quasi-static and dynamic measurement, piezoelectric can do both. Obviously, it's optimized for dynamic measurement, which means that you can measure short pulses, long transient events, sinusoidal events, this type of thing. Very dynamic, anything dynamic. And you can see here quasi-statically that, well, maybe this picture is blocking you, but there is if you have a static event, the quasi-static charge amplifier is able to measure that as well. Obviously, with any piezoelectric system, the charge amplifier will generate a small drift over time. And when it's in a quasi-static mode, very common, people understand that. And in a lot of cases, if you're measuring large forces, it's really not going to be an issue. If you're trying to measure small forces quasi-statically, it can become an issue, but there are other ways to compensate for it and get usability out of a piezoelectric solution for both quasi-static and dynamic. And here's just an example of quasi-static again. I'm just going to go through a little bit. The drift component that I talked about is roughly around 0.5 Newton per minute. So if you're measuring hundreds or thousands of newtons, measuring over a minute, that's almost insignificant, or it is insignificant. So and a lot of times you can compensate for this as well. So even for static events or quasi-static events like thrust, it's usually not an issue with regard to measuring with piezoelectric technology. Strain gauge technology, we absolutely talk to a lot of folks, a lot of engineers and scientists who are very intimate with strain gauge technology. Now, this is basically using a Wheatstone bridge capability where the change in resistance is proportional to load. So you basically work on a flexure basis where as it flexes, it changes the resistance of the bridge, and that relates to the load. purely a static measurement technique. However, it does have some dynamic capabilities depending, but it's probably known most for its low frequency characteristics. You know, it's often hard to do a comparison between technologies, but I try to take a stab at this, and just to give you a perspective. Obviously, the best for static measurement is strain gauge. The best for dynamic measurement is piezoelectric, as I said. Piezoelectric has wide measuring ranges for sure. It's usually much smaller than a strain gauge sensor, has quite a good lifetime, cycle lifetime. It doesn't rely upon flexing or it relies upon stiffness. Whereas strain gauges usually have very good temperature compensation capability, very good in temperatures, very good in harsh environments, and accuracy, because it's usually quite good, you know, compared to piezoelectric as well. And again, it depends on the application, really, and you know, these check marks can change. That's why it's often so hard to compare. But basically, the main takeaway is strain gauge is primarily optimized for static and can do some dynamic. Piezoelectric is optimized for dynamic and can do quasi-static. So a little bit more on the terminology. Piezoelectric IEPE. Piezoelectric means that there's an external device called a charge amp, which actually converts a charge signal, electrical signal, into a voltage, plus or minus 10 volts. And basically this measuring chain, piezoelectric, is completely rangeable. Unlike a strain gauge, you're often getting the strain gauge size based upon how much mass you have, how much dynamic or how much force you expect, and you live with the resolution. With a piezoelectric solution, you basically, you know, size the measuring chain for the dynamics of the event, quasi-static or dynamic measurement of the event, not necessarily the size of the load cell, if you will. It's not based upon the capability of a load cell. It's based upon the performance is based upon the how you range the measuring chain. So it's completely different concept in terms of performance. The IEPE is when you have electronics in the sensor, and that gives you purely dynamic capability, often used in accelerometers. If you've ever used a piezoelectric accel, it's usually going to be they call it ICP or IEPE. Those are common terminologies. In terms of frequency response of piezoelectrics, quite easy to understand. It's a single order high pass characteristic on the low end, and it's a lightly damped second order system on the high end. What that means is that you can write a set of closed form expressions to relate the frequency of the amplitude response relative to the natural frequency of the system. So if you wanted to know the 5% frequency of a 5% amplitude response of a piezoelectric sensor, you would simply take the natural frequency divided by 5, and 10% would be the natural frequency divided by 3. So what a 10% response would be is that's where the amplitude response varies plus or minus 10% over a given frequency band. That's very helpful in terms of measuring some high frequency or some frequency events, harmonics, and so forth. On the low end, it acts like a single order high pass characteristic, and that in the Laplace domain is given by this famous expression. Anyway, you can calculate closed form expressions for the frequency response in terms of the time constant, and you can relate what the effect of this roll off is at low frequency. So in a piezoelectric, you're usually dealing with something that's AC coupled, and even in quasi-static measurement, you're eventually going to not be able to measure anymore over time. It's going to have a limit eventually. So for short duration, for medium duration events, piezoelectrics are widely used. Some applications: micro vibration and thrust tests. Certainly, force limited vibration and propulsion test is another application that we often come across. The rangeability that I talked about. Simple example here where you have a sensor that's rated for 10 kilonewtons, and you have a charge amp and you have a cable. So in this scenario, you can easily range the measuring chain for 10 kilonewtons or 1 Newton. And you can see that the broadband noise actually scales as a function of range. So you're not, like in a strain gauge device, you would be taking the resolution of a 10 kilonewton sensor. In a piezoelectric device, you take the resolution of whatever range that you set up in the charge amp. Totally different concept, but very powerful. It's almost magical in some ways, people say that to me. A lot of times also in piezoelectric systems, you tear the measurement, meaning say you had, I don't know, 100 kilograms of mass acting upon a force sensor. You just reset the amplifier, the actual electrical measuring chain thinks you have zero mass on that force sensor, and now you just range the measuring chain based upon whatever event that you're trying to measure. So it gives you even better resolution because you can tear out any static masses, which is pretty powerful in terms of piezoelectrics. Also, with regard to dynamometers that I mentioned, dynamometers are basically force plates with multiple 3-component force sensors in it. They basically act as a spring mass system. So with any spring mass system, if you add mass, you're going to reduce the natural frequency. And this is a physical rule. Okay, it relies, the same for strain gauge as piezoelectric. So keep that in mind as you're building a capability to measure certain frequencies. A lot of times, if you need high frequency measurement, piezoelectric is absolutely the first choice. And a lot of times, added mass doesn't have as big effect with piezoelectrics as it does at other technologies. So it's something to think about when you're taking your measurement. Then there's also microvibration applications and some things that make it very interesting in terms of the space industry, understanding how mechanisms operate. I mean, mechanisms could be robotic systems, it could be reaction wheels, could be cryogenic coolers, it could be antenna systems, actuators, and so forth. I mean, throughout Canada, there's quite a bit of work going on with a lot of robotics and certainly antennas and other technology that's put on satellites. So what's of keen interest to people, of satellite engineers, is how much forces from these mechanisms and how much moment is really affecting the actual satellite itself. Well, to really characterize that, you need a system such as what I'm showing here. It's a force dynamometer, and these could be upwards of say 400 millimeter square, okay, or even bigger, okay. And they, because they're made with ceramic top plates, ceramics tend to have a very low density, so half the mass of steel, and a high modulus of elasticity, so a high stiffness. Higher stiffness of steel. So it gives you such capability in terms of measuring low forces. It's really the right way to go when you're trying to really get a large platform and measure very small forces. As we show here is, the basic resolution of some systems like this is on the order of a millinewton in terms of broadband noise, and about a 0.5 millinewton meter, also broadband noise for moment or for torque. So very sensitive. And when you get into these applications, they certainly require paying attention to seismic events and all kinds of other events of the facility, that could actually disturb the measurement when you're measuring such low levels of force and moment. In terms of mechanisms, I mentioned there's quite a few different mechanisms out, that are of interest and characterizing cryocoolers, as I mentioned, positioners and antennas, reaction wheels. I'm going to talk probably on those three, and then there's quite a few others here that I've mentioned already. Some I didn't, but there's quite a bit of opportunity to try to understand how mechanisms affect satellite performance. And that's very much at the interest when you're doing exported force and torque measurements. So with exported force and torque, it's not just a vibratory event. you could actually have a transient event. Say it's a optical shutter or a release mechanism. All these create impulsive or transient events on the satellite, and they also have to be understood. And it's extremely challenging sometimes to measure these transient events and characterize them. And I have an example later on anyway of what some of the things of tools of consideration that need to be performed. I mentioned a reaction wheel, and what a reaction wheel is, it's basically a device which provides attitude control to a satellite without the use of propellant. So it's quite important because there's just no way to bring enough propellant on a satellite that's going to operate for years. Okay, so you need some other method, and this flywheel type design can be used to compensate for attitude variations and for pointing. Oftentimes, reaction wheels are integral to any attitude control system on board a satellite. As they rotate, these are rotating mechanisms, they all have jitter. They all have exported force and torque, disturbances. So oftentimes what's of interest is how much jitter is occurring in a reaction wheel. A lot of times these reaction wheels are precision balanced to minimize any imbalance so you don't have a wide disparity of jitter. Obviously, if you have high vibration imparting into the satellite, you're going to affect any imaging system, okay? So that's the other thing, and that's what this illustration shows, is that you have a bigger centroid of vibration. You're going to blur the image, if you will, if you have an imaging system on board, or a pointing system is going to find it hard to point accurately given a high amount of jitter. So it's very important you characterize that on the ground here, and that effort is forever ongoing. Typical system for a reaction wheel test uses this dynamometer and a charge amp that I mentioned that converts the signal to a voltage, plus or minus 10 volts, goes to a data acquisition system, and you use a display software to see the results. Well, in this case here with reaction wheels, oftentimes you're looking at both static and dynamic imbalance, where you're looking at either the forces or the moments and trying to quantify the magnitude of those events. The plots you see down here is very typical of a reaction wheel test, where they call these waterfall plots, okay? And you're basically looking at the amount of force or moment versus speed versus frequency. And you can see here there's a primary ridge, and that's associated with the static or dynamic imbalance. But there's also other ridges here on the waterfall plot that usually are related to things like bearing vibration, for example. Cryocoolers basically are used in satellites to cool detectors. Could be an IR detector, gamma ray, X-ray, and imaging systems. So they're very integral to doing a proper imaging solution. With that said, cryocoolers are comprised of pumps and mechanisms that rotate, so they can be quite noisy in nature. So there's a large effort either to do passive or active compensation with cryocoolers. Passive compensation I'm going to address here in the next few slides, and then the active compensation is something that people will do to actually monitor the vibration and then adapt how the cooler actually operates to get less vibration, okay, but still achieve the mission goal of cooling. So it's a careful balance for sure. This test here we did at the Utah State University. We have a Center for Space Research, and there was a 6U small sat or CubeSat that is being worked on, and this was the cryocooler for that. Anyway, it just shows roughly how a cryocooler would work. You have the heat in through the detector. You have a cold finger through a thermal strap. That goes to a heat exchanger system, which basically cycles Cryocooler, then a motor to a radiator panel, which basically gets the heat out. So heat in, heat out, everything is cooled, and then by cooling the detector, you're going to optimize the performance of detecting small changes, and that's very critical. So the passive technique I mentioned is wire rope isolators, and these are basically what it sounds like. They're made of braided stainless steel, and they're very passive in nature, and you basically mount the entire cryocooler assembly on these wire rope passive isolators. As I mentioned, there's a cryocooler loop, there's a thermal strap, there's an optical detector right here, heat exchanger and pump, rotating fluid joint, and radiator panel. There's also, at this point here, a particle damper, which basically is mounted at the cold tip, which is intended to mitigate some of the vibration at the cold tip. And then I already mentioned the radiator panel. This is an example of some of the testing we did using the dynamometer. And I don't know if you can see that picture, but that's the radiator panel circling around. You have the cryocooler here, you have the thermal strap. We have an accelerometer on top of the cold tip, and we have a 3-component force sensor at the end of the thermal strap. And then we have underneath the entire cryocooler is a dynamometer, a multi-component force measurement system. And you can see here the wire rope isolators were just blowing up on right in this spot here. So that's sort of an overview, and that's just a top view on how everything goes. I'm not going to go through everything, but this is the bus for a 6U CubeSat, and very typical. This project was sponsored also through NASA. Some results, and again, these are sort of preliminary results, the testing going on, but basically the black section is when you have everything locked down. You have everything hard mounted, and the red section is when you have it on these wire rope or passive isolators. And what you see there is that the passive isolators actually bring the vibration level down substantially. And this is really the total cryocooler assembly. We're underneath the cryocooler assembly. So very successful, I think. The passive isolation did a quite a good job, I think, in this case. And certainly that was forces, and this is for moments, and you see generally the same trend where the vibration is mitigated by use of the wire rope isolators. This one here is actually at the cold tip of the cryocooler assembly, and using the accelerometer. What you see here is basically sort of the opposite. You see that the actual vibration is actually more at the cold tip end in this case, and we trace that back to the wire rope isolators actually amplify less than 100 hertz. And out at the cold tip, what we noticed was that there was, if you could see the frequency response here to the right, there's actually a significant harmonic right around 90 hertz. So you definitely have more development to be done on the wire rope isolators for sure. But again, it's a passive tool, and you need a combination of that and also the particle damper at the end of the cold tip to achieve a good performance in vibration. Then at the end of the thermal link, we see that something more normal. The thermal link is on also, or the detector is on on the wire rope isolators as well, and we see also a good attenuation of vibration with this system. So very encouraging. So again, this is say very typical of how scientists and engineers will characterize mechanisms which are going to be flowing, and they need to understand how they actually work in space and how they affect the satellite itself. Positioning mechanisms, okay? I mean, positioning mechanisms, gimbals and stepper motors. I mean, when you're talking about satellites, there's all kinds of, there could be positioners relative to robotics, could also be to antennas and gimbal systems to, do communications and so forth. So it's very important to try to understand the exported force and torque of those mechanisms as well. Well, in this case here, we used a similar but different scenario where we use a smaller dynamometer, but much like the system we showed you before with a charge amp, data acquisition, and so forth. And you use various antenna systems. As overall gimbaling basically are used commonly to point antennas, to achieve high link integrity. So a simple example, when you're using stepper motors, in this case, it's always important to have a very low mass antenna. Obviously, mass is very critical when you're out in space and actually launching payloads. You want to always pay attention to mass, because that relates to thrust, at least thrust. And then what you see here is in the normal mode of operation, the stepper motors didn't seem to present much of a disturbance, but in the fast mode of operation, what we saw was much higher levels of excitation or jitter. And what we attributed that to is that the actual stepper motor in the fast mode was actually exciting the structural resonances of the antenna itself. So as antennas want to be made lightweight, there's also a trade-off. Lightweight often means more flexible, and the resonances need to be designed in so that they do not become problematic for actuator systems as well. So these types of systems that I show here are very integral to looking at how to develop positioners and gimbal systems and devices that need to move in space, because they're going to generate jitter as well to the satellite. Then I talked about release mechanisms, and I just wanted to point out, when you talk about transient events, you always have to think about the inverse proportionality rule. And what that means is that the frequency extent of a transient event is roughly proportional to the inverse of the duration of the event. Okay, so what I show here is there's a rectangular pulse and say a half sine pulse. And if you look at the traces down here, these are just basic FFTs. And you can see here, maybe in the one furthest to the right, that the actual energy of a rectangular pulse is actually quite high in frequency, because these sharp edges actually have to be represented by high frequencies, whereas these rounded edges do not have as much energy or power at the higher frequencies. So if you were looking at a rule, you would say, well, a rectangular pulse roughly has a 90% of the energy at about 0.85 over t, the duration, but 99% of the energy over 10 over t. So you can see the wide bandwidth. So if you had a 1 millisecond pulse, 1 over 1 millisecond is a kilohertz, 10 times 1 kilohertz is 10 kilohertz. So you get a wide frequency really quickly with transient events. Whereas if you have a half sine pulse, rounded edges, the 99% is slightly over 1 over t. So most of the energy is in that first 1 over t region, which is exactly what you would want and expect, at least in transient events. So with transient events, always keep in mind that you have to have the right measurement capability, because if you have a event and you use that 1 over duration rule, say you have a 1 over 1 millisecond, and that's 1 kilohertz. If the natural frequency of your measurement system is less than 1 kilohertz, your resonance of the measurement system is going to be buried into the measurement of what you're trying, or the trace of what you're trying to measure. So it's really tricky to measure transient events with, say, force sensors. You have to really understand the duration of what you're trying to measure, the characteristic, and really look at your force measurement system critically to get the maximum frequency out, so you get separation between the event duration, 1 over that, and the resonance. So it's, I think, one of the more challenging problems. And I come across it quite often, actually, because there's plenty of companies that are looking for transient events, optical shutters, release mechanisms, and trying to understand how they affect satellites is very tricky at times. Okay, so force limited vibration. So we talked about micro vibration or exporter force and torque. In the area of satellite development and test, there's always a recognition of, geez, what kind of vibration is this payload going to see? I read this paper some years ago, and I just fell in love with this slide. Okay, this chart that the authors showed, is it shows really the life of a payload. Very graphically, but almost like a cartoon. But it just shows that eventually, at the initial stages of the liftoff ignition, you've got some fairly high level vibration. Then as the payload is deployed out in space, you've got separation events and so forth, and you can see those as transient, high amplitude events that have to also, the payload also has to survive, and eventually the payload is deployed. So how do space companies deal with this? Okay, if you're developing satellites, how do you deal with it? Well, you need to understand that during, say, launch and flight, there's considerable levels of forces and loads and vibration on those mechanisms or on those assets going to space. This was a case that was done with a GLASS mission. They actually put up, measured with accelerometers and force sensors. And they found, just look at the forces. You're upwards of, this slide doesn't have newtons. I'm really apologize, but 5,000 pounds is around 20,000 newtons. Okay, on that order. So it's significant. All right. So keep it in mind that the payload itself has to survive this. And so how do we test for that? Well, the area of force limited vibration was developed back at NASA Jet Propulsion Laboratory back in the 90s. And basically what it attempts to do is use a vibration control system to monitor the fixed base resonances where the satellite and the shaker are actually interfaced, actually connected. And by doing that, you can actually limit the amount of force going in at resonant frequencies. And the purpose of that is really to better represent or better test to the actual flight conditions of the payload. The actual payload is actually mounted on a fairly compliant structure. And with regard to a shaker, it has near infinite mechanical impedance, whereas the actual structure that the satellite or payload is mounted to is quite a bit less impedance. So, we have to monitor, we have to be able to simulate those conditions so we don't put energy into the payload at those resonant frequencies, because normally they wouldn't be present in an actual flight. So that's the basic rationale behind using force limited vibration. It's really simulating the actual launch conditions of the payload. And also you need a very capable extremal control system, which could look at multiple channels of acceleration and force and trying to limit forces based upon the maximum of a given channel, say. And those limits that would be used are really tied to legacy flight data, analysis, and certainly added safety margins. So this area is actually quite popular, and I would say most payloads and components go through a force limited vibration test nowadays. There's still a response limiting used, and in some cases it could be used, but I'd say the norm is force limited vibration testing for space hardware. And this is just an illustration of what this would look like from a NASA report. You basically look at the actual envelope of the vibration spectra, and in this case here you would see the unlimited input force would actually be maybe 10 dB higher than the envelope. So what force limiting would do is actually notch that at that frequency and would do it automatically based upon monitoring the fixed base resonances of the structure to shaker interface. Pretty cool. a project we were involved in anyway, from an instrumentation perspective. Obviously, NASA did all the work. We basically, talked about the instrumentation itself, but this was an observatory, fairly large. I mean, upwards of over 3,000 kg. Certainly the force ring, and what you see here is a head expander or force ring where the force sensors are actually mounted between this interface here, and you can almost see them in this gap here. So the ring diameter was around 2.6 meters. There's 12 sensors. You've got to preload everything and mount it, custom bolts, and the frequency of interest was like 5 hertz to 70 hertz in this case. And obviously you wanted to measure both forces and moments in this case, and in some cases limit on moment, overturning moment. This is just a quick schematic of what it might look like. And if you look at this geometrically, you can actually compute closed form expressions of fx, fy of z, and mx, my, and mz. So you can easily do this. And now by having these expressions, you can now measure directly forces and moments in 6 components for these force dynamometers. This is just a simple example of some guidance that we sometimes use when talking to various application engineers. What type of maximum shear forces can you handle? What sensor are you using? What kind of bending moments? What kind of overturning moments can you handle? These are all very important, because damaging a test article is one of the last things you want to do, and you always got to have sufficient margins built in, and certainly safety and guarding against damage or catastrophe is always critical. The force ring, I just showed a picture here. There's a lot of detail between putting together such a dynamometer. You have to preload the force sensors. You have to then make sure they're aligned. You got to also calibrate those force sensors in situ, okay? And that's also an important part. So when developing these complex force rings that monitor the fixed base resonances, there's quite a bit of detail involved, and we can certainly answer any questions with regard to doing such work. So what do you do when you get everything sorted out and put together? You've got to calibrate it. And the technique of typically used is one that where you use a low frequency sweep or a dwell below the first resonance of the vibration fixture, and you're comparing the apparent mass, force equals mass times acceleration, to the total mass. So you would have calculated the total mass acting upon the force sensors, and then by vibrating it below the first resonance, you'll get the apparent mass by measuring the force output and the acceleration output. You compare the two, and then you put in a correction factor based upon the difference. Typically, the difference is somewhere between 5 and 10%, which is quite normal for these installations. If you get something in the 30 or 40% difference, it's usually because you did something wrong. Maybe you made a wrong calculation on mass, or maybe something's broken, which is something to find out early and later. So now we go to like measurement noise considerations, and I talked a little about micro vibration already, but anyway, there's a lot of sources for noise, and some of them are related to electrical, ground loops, or electromagnetics perhaps, or battery, or AC power to DC power conversion. And obviously wider bandwidths have directly proportional to RMS noise. So all these things factor in the electrical noise. When doing microvibration, there's always issues to do with seismic noise inputs, structural response of the test rig, acoustic borne noise. Okay, if you've got high level acoustics, you can actually excite the measurement structure, the actual table, and maybe even the test article itself. So a lot of detail there. So when using DC power charge amps and signal conditioning data acquisition, we reckon that you can get upwards of, I don't know, a few dB, 6 or 7, 8 dB improvement in noise by virtue of just using battery power. So a lot of times what we'll do is we'll recommend to customers that end users, hey, look, really consider using a battery, because what a battery will do is it will reduce the overall noise, but it'll also take away any other harmonics caused by the AC to DC power conversion process. When you're looking at harmonics of test articles, it really becomes hard to separate harmonics of AC to DC power conversion to harmonics of actual mechanisms sometimes, okay? So it's always good, and you can see harmonics here, in this trace here. So, these are basically due to the power conversion process. So it's something to keep in mind that if you really want to clean spectra, noise spectra, using a battery source is very helpful. And when you're doing a lot of these the micro vibration measurements, a lot of times you're looking at vacuum chambers. In cryocoolers, a lot of times you want to mitigate sound transmission, which doesn't transmit through a vacuum, so you don't get any issue with exciting structures. In thrusters and propulsion, the actual amount of thrust is oftentimes higher in a vacuum than in air. So a lot of times those things are of interest, and users want to actually test their test articles in a vacuum. Well, to do that, you have to have the dynamometer, you have to have the proper cable, low outgassing, you have to have a vacuum feed through, and certainly the equipment outside the vacuum chamber. In terms of doing vacuum testing, it's always important to have what's called low outgassing components. And what outgassing is, it's actually, what it appears to be. It's actually some materials actually disperse material that actually can be deposited on very sensitive optical systems, for example. So pre-baking or doing a thermal vacuum bake-out is often one of the first rules of anything before you put any sensitive hardware into a vacuum chamber and any instrumentation. So low outgassing, very critical to vacuum measurement. I mentioned before about force limiting, and the actual M+P system is a manufacturer of vibration controllers, and these vibration controllers actually can control on RSS vectors, some force notching, as well as overturning moment notching, and they're fairly complex systems which can take in hundreds of inputs and control on any one of them, okay? And it's quite sophisticated. So I recently gave a webinar with M+P on this technology. You can look at the Kistler website if you're interested in more information on that, or talk to our Mississauga office, and they can put you in touch with the right material. This is just an example of what a force limited test might look like with a M+P shaker controller. You have force sensors, you have signal conditioning, which basically takes in the dynamic nature of the test and basically puts every channel into the M+P shaker controller, so that that system will actually compute the forces and moments and the overturning moments, all the vector forces that need to be controlled. So there's no need to necessarily have those closed form expressions at hand. What's more important is the M+P shaker has the geometry of the sensors you're using, of the vibration fixture, and then it automatically will handle the calculations. And that's more or less nowadays what goes on. Not all the time, because it really depends on the sophistication of your system and controller. Some folks don't have the high sophistication as of yet, and it's always a money issue sometimes, a budget issue. And eventually that does happen though over time. Thrust testing, is another application. I showed one early on. Basically, there's a couple different propulsions out there: chemical propulsion, electrical propulsion. Very popular now. I think over the last many years, you've seen more and more development with electric propulsion, space propulsion. I would say because of the long-term and low force capability of electric space propulsion, it's not really optimum for piezoelectrics, whereas chemical propulsion tends to be more optimum for a piezoelectric solution. as I mentioned before, I mean, there's all kinds of different tests in propulsion. It might be characterization of thrust, looking at different nozzle designs, specific impulse capabilities to assess efficiencies. You could also be doing pressure monitoring of the combustion process, or in both static and dynamic pressures. Could be looking at vibration. You could be also looking at thrust measurement and thrust misalignments. So all these different aspects of propulsion testing have different sensors that you would need to accomplish. Obviously, when you get into these types of scenarios, it's often good to talk to an application engineer. Like I said, if this is of interest, you give the Mississauga office a call, and they can certainly give you the proper information on any of these applications. But in the meantime, we're going to just touch upon a little bit more detail, just so you'll walk away with a little bit better perspective. And I work a lot with folks who I cover the Americas, as Chris had mentioned. So, you know, that's a pretty wide region. And there's quite a bit of use still of strain gauge. And in that regard, you know, I often ask for feedback. I said, hey, you know, why would you want to use a piezoelectric versus strain gauge? And one of the engineers I work with, I guess, is probably one of the most power users I know for piezoelectric. And he also uses strain gauge. But he basically says, you know, strain gauge is a much lower natural frequency and inherently, noisier, in his opinion, than a piezoelectric. He felt that there was more mechanical noise due to the flexure capabilities of a strain gauge platform compared to a piezoelectric. Also, response time, because the piezoelectric had much higher bandwidth, much higher stiffness, could really respond to short duration burns, and as such, so you get more fidelity in your measurement. And then the last thing he mentioned was test stand adaptivity and adaptability. And what he mentioned there was he can get modules of force links or force sensors and basically build up different capabilities every time. And it's just a simple in situ test to calibrate it. And he's measuring very quickly. So he explained to me the time his technicians take to instrument is actually quite important to him. And he wanted to find other ways to reduce this time, because the more time they're putting things together and calibrating, the less time they have to do to test. So this is the feedback from one user anyway, and it's something to take in mind. Other things, and I mentioned a lot of these already, but thrust characterization, where you have basically a force platform that's measuring the actual thrust. Okay, and a lot of times these are multi-component force platforms. You're looking at fuel efficiency, you're looking at nozzle designs, you're looking at overall impulse of the engine, and certainly the amount of thrust, and maybe even thrust misalignment in these types of applications. There's also measuring static pressure. As I mentioned to you before, measuring static pressure for long periods of time. Well, you know, piezoelectric might not be optimum for that. In some cases, piezo-resistive technology is used on a standoff to reduce the temperature of the measurement. So in some cases, you need more than just a piezoelectric solution. So a piezo-resistive solution to measure static pressure in the combustion chamber. Again, here is another combustion instabilities, another application. This is where you're actually monitoring the pressure inside the combustion chamber, and maybe even having a high temperature accelerometer as well. So you can imagine 700 degrees C would be really the requirement you would need in a sensor to be able to accomplish this. And piezoelectric technology certainly satisfies 700 C continuously, very high performance capabilities to measure pressure and vibration at these temperatures. Liquid propellant and fuel supply is measuring this with, it could be valves, Cryopumps all need pressure sensors, cryogenic pressure sensors, and accelerometers to measure both pressure and vibration during operation. This is a very common application. Going down to LN2 is pretty standard, but in some cases you even have to get colder depending on what propellant is being used. Certainly ignition systems, understanding sometimes it's a electric spark or a chemical ignition, but understanding when ignition occurs and how that's correlated with all the other aspects of propellant delivery is very important. Also with rocket engine applications. And just briefly, we'll talk a little about maybe a few minutes on acceleration, vibration, shock. Basically, all these terms are very common. You listen to people talk and they're talking about acceleration, vibration, shock. They all are measured with accelerometers, okay? But they all mean something different. Acceleration could be both a static and dynamic event. Okay, you can see here there's times when you have static acceleration or constant acceleration, and you have varying acceleration. So in this sensor, you would need something fairly special that can measure both static and dynamic vibration or acceleration and vibration. It's certainly an AC coupled dynamic event. And shock, as I mentioned, is a short duration transient event that basically is going to go by the rule that I mentioned before, the 1 over the duration in terms of frequency. And that's always something to keep in mind. So with these types of applications, there's always different crystals involved. As I mentioned in the beginning, piezoelectric crystals basically convert mechanical to electrical. But there's also very high demands in terms of application. I mentioned previously where you have an engine, a rocket engine, you might be up to 700 degrees C. You might be flying an aircraft and you're up at altitude and you're at minus 75 degrees C, okay? So you have a wide range of temperature operation. Well, it's always good to have a crystal, a piezoelectric crystal with very good performance with temperature. And this PiezoStar technology anyway has almost nearly flat performance with temperature, meaning flat sensitivity deviation with temperature, whereas other technologies would tend to have some deviation with sensitivity as you vary in temperature, either hot or cold. So always keep in mind that no matter what sensor you're using, it really depends on how it's constructed and what materials are in it. Really gives you the actual performance of the sensor. So even though it might look the same as something else, it could be quite a bit different based upon how it was constructed. So it's always good to look at the data sheet, talk to your favorite application engineer, ask your questions, and certainly make your own opinions at that point. Cryogenic solutions, I mentioned some applications already where you're dealing with cryogenic vibration or cryogenic forces, pressures. So in all these measurands, piezoelectrics can support cryogenic test. Typically down to LN2, minus 196 C, but in some cases, some scientists and engineers have used these even lower than that. 4 degrees Kelvin, for example. I can remember 1 or 2 people using selected sensors for those applications as well. Lightweight cabling solutions, as I mentioned before, when you're talking about satellite mass and payload weight, it all relates to the rocket design and getting out in space and deployed. So you're always looking at minimizing mass. In a lot of cases with vibration test, you can't get to the sensor to remove it after the test. So you basically cut the cable, terminate it, and you're leaving cables and sensors in the payload, in the satellite, while it's on its mission. So for one, you need low outgassing. For two, you need low mass. So there's a lot of technique to getting low mass cables and high performance. So certainly some of the things we've introduced is M4.5 connector technology, metric 4.5 millimeter, and it really reduces the weight substantially and doesn't compromise any on performance. It's pretty amazing, and that's been used for quite some years for these types of applications where you need to fly accelerometers and cables after the test is done. You've seen this picture before. Obviously, anything to do with vibration test. I mean, a lot of times you're instrumenting payloads with accelerometers as well, and using electrodynamic shakers. A lot of times it's outside the satellite. Sometimes they're buried in the satellite. So those cases, you don't usually open things up and take things out afterwards. So there's a certain amount of test instrumentation you could remove. Certain amount you need to leave in there. Mechanical characterizations, I mean, in thermal vacuum chambers, very common to understand how payloads deal with cold and vacuum and what the effects are, and monitoring that in vibration. I mean, some years ago, we did the James Webb Space Telescope, JWST, used very high sensitivity sensors to monitor cryogenic vibrations in these vacuum chambers. So very special technology that needs to be used for such applications, but certainly achievable results. In terms of ESS, anything to do with environmental stress screening, looking at ways of eliminating production problems or premature failure conditions are all being tested extensively for the space industry, and a wide range of accelerometers are used to accomplish this. So we're nearing the end here, almost at an hour. So what we've done is we've looked at measuring chain. We've talked about measuring chains and rangeability for piezoelectrics. We've talked about microvibrations up to high level force, thrust force, and low levels down to millinewtons. All very achievable with the rangeability. We talked about dynamic and quasi-static capabilities, very much regularly used in piezoelectrics. The modular design of piezoelectrics really reduces the time to put together test fixtures and to actually test and calibrate, leaving more time to test and making the technicians more efficient. Vacuum capable equipment, low outgassing. In the space test area, you must have vacuum compatible equipment and to be able to accomplish those goals, and certainly wide temperatures from cryo to 700 degrees C. So you can see piezoelectrics really adds a layer of technology to the engineer, to the scientist to consider, when he's trying, or he or she are trying to make a proper measurement. On that, I'd like to thank you all. It was very much a pleasure to address CASI's members, and I welcome any questions at this point.
Bill, thank you so much. That was really fascinating. I have to admit that it's a long time since I've had anything to do with measurements. Data acquisition, experimentation takes me back to university days. I haven't had much to do with it since then, but this was a really nice refresher of all the things you have to consider, and really eye-opening too. So thank you so much.
My pleasure, Chris.
We do have a couple of questions in the chat here. I've been watching it.
Okay.
Oh, my chat has disappeared. Hold on. There we go. Okay, so we have a question from Blago here. Are there any physical size limitations to these sensors, small or large? And what drives the size constraint?
Very good question, actually. Usually the size is driven by load handling, okay? Typically, the larger sensors can handle higher loads and usually are more stiff than most. So remember the rangeability issue. So even though you might get a 50 kilonewton sensor, you can still use it to measure a millinewton with no compromise. So sensors usually grow in size when you talk about load handling capability, but you don't compromise resolution because it's all rangeable. And that's, I think, the key takeaway with piezoelectrics.
Okay, and Blago's question continues. He says, is it the crystals? Also, are they the crystals that Kistler uses naturally occurring, or are they synthetically manufactured?
Wow, very good question. Well, quartz is actually naturally occurring, but we don't use such quartz. We actually grow quartz and grow some other crystals in very controlled autoclave environments. And the reason why is that in our experience, we've been doing this for probably 60 years plus, the purity of quartz, of a piezoelectric material is very critical and to get the best performance. And in fact, when we grow quartz or any other piezoelectric material, there's actually a production center that actually takes it, aligns its primary axis so it can be actually cut and processed into the shapes and sizes and that we need to make sensors. So you can think of quartz growing, but there's also actual manufacturing of piezoelectric materials to go into sensors. There's a lot of machining capability and high tolerancing, high surface finish criteria and so forth. So it's there's a lot behind that. But yeah, the crystal is all grown in controlled environments, and it's all carefully monitored and carefully handled and processed to make sure it's at the highest quality for the best performance.
I'll just add a question to that. When the crystals are manufactured, can they be very precisely tailored in the growth, or is there a lot of wastage? You talked about finishing the surface and so on.
It's a good question, Chris. There's actually, it probably depends on the crystal. And quartz, I would say it's really I'd say fairly high efficiency. We get a lot of use out of the quartz that's growing. I'd say in other say more custom materials, there might be more that we'd have to say compromise on where there's less material to use, and you have to then maybe have a little bit more scrap in that case. But I'd say generally they're all very efficient, and it's part of what at least we do. We spend a lot of time on manufacturing technology and making sure that we get the highest usage out of these materials because they're so costly to use or to develop. So I would say in general, the takeaway I would say is it's generally well under control. But yeah, in any manufacturing process, it might be that there's a bad day. It does happen.
Okay, here's a question from Jeff. Are there integrated means to diagnose failure modes in these sensors? Sorry. Yeah,
pretty. I'd say the one of the main failures we see is, I'll say from time to time, is an insulation resistance failure, which can easily be identified by what we call an IR tester. So it's an external device you hook up to the sensor, and it quickly tells you in how many ohms of insulation it has. And that would be for a piezoelectric. For IEPE sensors, ones with electronics inside, they generally have to have a bias between, say, 11 volts plus or minus 3. So if the bias level is not within that range, it's usually damaged. And then lastly, you can always test it, on a shaker or on a force, test stand to just make sure that things are linear. But generally, you can use some external device to check if it's operational. But in general, you'd want to also test, maybe do a functional test on it to apply a force or vibration. That's the surefire solution. With strain gauge, obviously you can do a shunt cal, and that sort of checks things. Piezoelectric doesn't have such a technique, a shunt cal technique, but there are ways to say get close to that using external equipment or maybe external ways of exciting the device.
And how about diagnosing failures once the sensor is in use?
Well, failures, can occur in terms of, if they do occur, it could be, that you see some anomaly on your data. You can see data falling out or something erratic. Okay, and that's certainly one indication that something is not working. Is it the sensor? Is it the cable? Is it the signal conditioner? Then there's a troubleshooting, and what we have is we usually recommend a certain approach going after these types of problems. And a lot of times, in my experience, sometimes it could be a cable, and maybe the cable was in a very harsh test before, and it was reused, and it wasn't checked out again, and you can see the effects of that. So I would say, yeah, it's troubleshooting is always a little bit, a little bit of training involved and coaching, but we can certainly, if the user wants to call us, and we can have a short chat and give some examples of how we would go about it, and certainly give our Mississauga office a call, and we'll be happy to address specific questions if you have certain concerns, for sure.
Jeff has another question. Have you some examples for where there was a collaborative process between a user and your technical people to develop new capabilities?
Wow, that's a good question. Well, that ceramic dynamometer that I showed you is really a collaboration between Kistler and actually a European company, and they came to us several years ago and said, "Hey, look, guys, we've got this hard problem. We've got these big things that we got to measure exported force and torque on, and we're talking 400 millimeters OD, and we need something to do it, but we need high frequency on top." And that sort of goes against all the rules of physics, right? You've got a heavy mass, you got a big platform, you've got all these facets going in. So we thought about it, and we said, well, we can't create new physical rules, but we can certainly bend the rules of physics. And by recognizing that ceramics had low density but very high stiffness, it basically solved the problem. Okay, we're not talking, when you're doing microvibration, you're not talking high forces. You're talking fairly low forces. So ceramic absolutely has the integrity to do a great job in that case. So I would say that was one example, but it happens probably more often. But yeah, I'd say that's one recent example of a development. And certainly a lot of times, we're working with customers and they're saying, "Hey, look, I'm getting this anomaly or that anomaly," and we find out, well, maybe we have to develop a special fixture or tool to help the guy align it better, or install it better. So there's those instances that happen as well. So I'll say one thing I can say, on the application side, since that's pretty much what I do, is we're often feeding those things back to the product managers on a regular basis when they come up, and we try to see if there's something that we can do to help. So yeah, that's a good question. So it does happen.
So collaboration is certainly not unusual.
No,
Good. Here's a question from Gary. Have piezoelectric pressure transducers been used for acoustic measurements, for example, in a wind tunnel to measure background noise? And then he adds, I'm thinking specifically of measuring unsteady pressures on, say, a cone model in a high-speed wind tunnel. The issue may be small size.
Yeah, I would say it's a very good question. It's certainly on our radar, okay? And there's certainly very small piezoelectric sensors with very high sensitivity. Absolutely is somewhere down the road. And I could tell you this from underwater acoustics. The sensors, and I did a fair amount of work back in the day on underwater acoustics. Pressure sensors are widely used for that, okay? These piezoelectrics. Trying to quantify, acoustic level noise. It might be a naval application where you're always looking at silencing and quietness of ships and processes, nuclear power generation of other pumps and compressors and so forth. So yeah, absolutely, they're used in these applications. But I would say from a wind tunnel, my experience has been more on the piezo resistive side at the moment. But what the application you mentioned, I'd say is one of those that I think once, say, a very small, high sensitivity sensor is available, it would be, I think, a keen application for sure.
Sounds like you and Gary should get together.
Yeah, Gary, give us a call.
I have a question of my own. I have a very small amount of experience with strain gauges for wind tunnel model force measurement. And I seem to recall that they were pretty cheap. You got them in sheets and glued them on. How does the cost compare for something of that size in a piezoelectric
Well,
sensor?
it's a good question, Chris. I would just say this is that type of strain gauges are really quite unique when you're actually bonding them to surfaces of structures and such. I would say there's I would say that's in a very special realm for strain gauges. It's really one of the niche areas that I would say. Piezoelectric doesn't have a normal way to do that, okay, that you can bond it to the side of a structure. I would say that's fairly unique to a strain gauge. But if you go back to wind tunnels, I mean, in terms of strain gauge, there are strain gauge balances that basically they use a multi-component force capability, and they mount a model on it and then expose the model to wind, and they measure the forces on with this balance. So on that, I mean, the pricing for that is comparable to what to what a piezoelectric solution would be. So maybe, yeah, comparable. I'd say comparable. There's pluses and minuses, I guess, but yeah, strain gauge can be sometimes less expensive depending on the application than piezoelectric. But again, does it deliver the performance and the requirements? Is always the question. Not any one technology that I know of can solve all the world's problems. So it's good to have an awareness of everything. So you might be faced with a problem that strain gauge just is really at the limits of, and piezoelectric is available, and it might be vice versa. So yeah, the purpose of this was really to, I often say, is to increase awareness, because as engineers and scientists, we often, once we hear of something, we can always refer to it sometime later on, and it might help us ask the right question at the right time.
A compromise, as always.
Yeah.
Here's a question from Lala. What kinds of soft piezo crystals you can suggest for PEHs?
Yeah,
I'm not sure what PEH means.
Yeah, I'm not sure either, but I would just say in terms of piezoelectrics, I mean, we deal with single crystal. We deal with crystals, and they're all, our design criteria is stiff. So I don't really know the answer to that. There might be others that look at softer crystals, but unfortunately, we are not one of them. So sorry, I don't know the answer to that.
Lala, perhaps you can clarify your question in the chat and we can come back to it. Here's a question from Jeff. Have you had any dealings with the NRC people in Montreal who are doing paintable PZTs that they have also used for temperature measurement?
Yeah, the PZTs, I mean, this is this is ceramics, okay? So it's a ceramic piezoelectric is really a is a synthesized piezoelectric material, and so no, I haven't had any experience with that. We don't make our own PZTs. If we were to use that, we would probably go to a foundry that would do that kind of stuff. But no, the PZTs are sometimes what you'll find is they're being used in some of the actuator type, piezo actuators, if that might be one of the things you're mentioning. But yeah, the piezoelectric technology, these ceramic stacks sometimes can generate some fairly large displacement and under good control. So that's one of the applications for sure. But PZT is also used in accelerometers, for example. It's very common.
Can you just clarify what PZT stands for?
It's I don't remember what it stands for, but it's It's just a class of ceramics.
Okay.
Piezo ceramics. It's a class of piezo ceramics.
Okay, thanks. There aren't any more questions right now in the chat, but I have another question of my own.
Sure.
How old is this technology?
Wow, that's a great
How far does it go back?
You know, it's a really good question, and I forget the dates, but I remember the slide I put together some years ago. But the Curie brothers actually discovered the piezoelectric concept back in the late 1800s, I think it was. So, but you couldn't really do much with it until the charge amplifier was developed. The reason why is that there's no way to really measure on a piezoelectric event requires what's called a very high impedance input amplifier to be able to generate a voltage, and that wasn't developed until I think the 60s when Walter Kistler actually developed the first charge amplifier, and hence the whole progression of the technology. Yeah. So I'd say maybe 50, 60 years in practice, but it was discovered maybe back in the late 1800s, the concept. But I'd say usability probably, yeah, since the 50s and 60s.
And a product of Mr. Kistler is, I guess, the basis for your company.
Yeah, it's one of them. I mean, he's very inventive. He just passed away recently at, I think it was 95. The guy, was creative as heck. I mean, just, you're really inventive, and those people are not so prevalent nowadays, it seems. But yeah, very inventive people.
I don't see any more questions in the chat right now, but if anybody else would like to add one, please do. I'll just make a little comment here, just to make everybody aware that Kistler is actually a CASI corporate partner company. They're a relatively new corporate partner, and I know that they've been keen to share their company capabilities with broader CASI community. So this presentation today has been a perfect opportunity for us to get to know you a little bit better. It's, I guess, not one of the big names in the Canadian aerospace industry. A lot of the corporate partner companies are household names like Pratt & Whitney and
Sure.
Bombardier and so on. But it's great to get to know one of our newer corporate partners.
Yeah, thank you, Chris. We really are excited to be partners with CASI. It's really quite a I think an organization that really brings a lot to the community, and we really appreciate that, and we welcome attending other events as they come out.
Jeff has just put a comment in the chat. He says, not so well known yet, in capital letters.
Thanks, Jeff.
So I don't see any more questions here. Perhaps that's a cue that we should be wrapping things up. It's 6:23, so we're just coming up to our hour and a half, but a very well spent and very interesting hour and a half. I'd just like to officially say thank you, Bill, on behalf of the Toronto branch, the CASI administration, and also all of our membership. Great to have you with us today. Thank you so much for it's taking a chunk out of your afternoon, not out of your evening, seeing you're on the West Coast right now. But thank you very much for sharing your company and your technological capabilities, and also obviously your enthusiasm for the work that you do. Could tell as you were talking and as you were describing things and your facial expressions on the camera there that this is something that you're very, very interested in, and you conveyed it very well to us. So many thanks for a very interesting evening.
Thank you. Thank you.
Todd, do you want to close with anything from the CASI end?
From the CASI end, we are happy to announce that we are going to be giving Kistler just the opportunity they're looking for, as we have just started accepting abstracts for Aero 2021. Maybe you'll get to see them there as a virtual exhibitor. As for this podcast, we will be releasing this on the website tomorrow at casi.ca/podcasts. Thanks everybody for joining us. We're really glad everyone was able to come together for this Toronto branch meeting tonight. And that's it for me. Back to you, Chris, if anything.
Thanks, Todd. I'll just say thanks everybody for attending. Watch your mailbox for the next presentation, and have a good evening.
Too.
Thanks.
Bye-bye.